today's lecture continues on the spectroscopy module that I have been giving for the last few lectures. Today we will talk about the polyatomic molecular vibrational spectroscopy, fairly elementary, and we will show a large number of animations on the vibrational motions as perceived by the spectroscopist. Let me recollect a bit of the diatomic molecular spectroscopy that we did in the last lecture. Okay. Let us start today. This is lecture 6 on spectroscopy, molecular spectroscopy, and we want to talk about the molecular vibrational spectroscopy of polyatomic molecules, vibrational spectroscopy of polyatomic, linear or non-linear. There is going to be a slight difference, and what we will be concerned for most of today's lecture is on normal modes of vibration. This is the theme of today's lecture, vibrations, and I shall use a program to show some of the animated motions, animated vibrational motions. Okay. Let me recollect the essential points of last lecture. Remember that when we discussed the diatomic molecular spectrum, vibrational spectrum, we started off with the simple harmonic oscillator model. It is a very useful model, and nevertheless it has its difficulties, and it is not applicable for molecules when they are in an excited energy state or when they are heated up to high temperatures and so on. The reason being that molecular motions, under the assumption of a harmonic oscillator approximation, the motion is restricted to small amplitude vibrations. Now think about the cases of simple molecules which have very strong bond. No problem with such cases like hydrogen chloride, carbon monoxide. These are examples that I have given. Several diatomic molecules, practically any heteronuclear diatomic molecule that you talk about. I also told you that homonuclear diatomic molecules do not show infrared spectrum because there is no change in the dipole moment of the molecule as they vibrate. The heteronuclear diatomic molecules which have a strong bond, it is very appropriate for us to consider the first few excited vibrational energy states as conforming to the simple harmonic oscillator model. And when this model is not really applicable, we also looked at the alternatives by allowing in our own theory the considerations of anharmonic motion. Recall the harmonic motion was half kx square in the Hamiltonian. The potential energy being half kx square, where k is the force constant of the diatomic molecule, was the harmonic approximation, and when we change when we include in the potential energy of the molecule terms like half kx square plus some constant times x cube plus some other constant times x raised to 4 and so on, these permit us to study the molecular motion as anharmonic, and the coefficients anharmonic motion, the coefficients C, C2 etc. harmonic motion, the C, C2 etc. they are called anharmonicity coefficients. Specifically, the motion C the coefficient C corresponding to the x cube term is called the cubic enharmonicity. The coefficient C2 corresponding to x raised to 4 is called the quartic enharmonicity, and so on. We also looked at a general potential in which all these enharmonicity coefficients are included, and the potential that we looked at was known as the Morse potential. The potential energy for that is given by some constant d naught into 1 minus e to the minus alpha prime x whole square. We used this formula, and we looked at the enharmonic vibrational energy levels and so on. This is for the diatomic molecule. Now today's lecture is to worry about the polyatomic molecules, where there are more than obviously 2 atoms, and there is a very simple formula for determining the number of vibrational modes in a polyatomic molecule. It is a very easy method to think about it. You can imagine that there are n atoms in a polyatomic molecule, and if each of the atom is free to move in any one of the 3 dimensions, the total degrees of freedom that the polyatomic molecule has is 3n. But you know that the atoms cannot move entirely freely of each other, they are constrained because they are bonded to each other, and therefore out of the 3n degrees of freedom, if we remove the constrained motions, 2 types of constraints corresponding to the overall translation of the molecule, that is all the atoms move in the same direction at the same time, then it is a concerted motion, and it is a translational motion of the center of mass of the molecule. That is one way to look at it. And there are 3 translational degrees of freedom corresponding to the 3 mutually perpendicular directions in a 3-dimensional world in which we live. There is also the motion about 2 or 3 mutually perpendicular axes that pass through the molecule, and these axes are known as the principal moments of inertia, principal axis of inertia, and the moments of inertia calculated about these 3 principal axes are 2 depending on whether the molecule is nonlinear or linear. A simple diatomic vibrational, the diatomic molecule has only 1 degree of rotational, has 2 rotational degrees of freedom. So considering these, for a 3n degree of freedom in an n atom polyatomic molecule, n atom polyatomic molecule, there are 3n degrees of freedom totally, you can remove 3 translational degrees of freedom corresponding to the motion about the 3 different mutually perpendicular axes. Usually we denote them x, y, z axis. And then there are 3 for a nonlinear molecule, or 2 for a linear molecule, rotational degrees of freedom. Therefore, the number of vibrational degrees of freedom in a polyatomic molecule number of total genuine vibrational degrees of freedom is 3n minus 5 for a linear molecule and 3n minus 6 for a nonlinear molecule, for a linear molecule and for a nonlinear molecule. Now diatomic molecule comes under the category of a linear molecule obviously, and when n is 2 there is only 1 vibrational degree of freedom, 3n minus 5, and that is what we went through in the last lecture, the previous lecture on the harmonic and the anharmonic motions of a diatomic molecule. today when we talk about the polyatomic molecule, the 3n minus 6 degrees of freedom will be described in the form of normal modes of vibration. Let me illustrate the normal modes by some pictures, and then we will explain what these things are and how do we understand them qualitatively. It is not possible for me to give you a quantitative description of the normal modes. It requires a little bit of mathematics and some basic familiarity with classical mechanics. I do not want to do that here, but I would like you to appreciate that the qualitative picture of how we visualize the normal modes of vibration as we see in the animations today. Please understand that within the approximations of harmonic motion, this is a very useful and is a very accurate picture of the molecular motion. We will also look at what are called group vibrational modes, or vibrations of groups of functional groups or certain sections of the molecules relative to the other, known as the local modes of vibration. Again, qualitatively I will illustrate this through the spectra that you must be familiar with when you look at the vibrational spectrum of polyatomic molecules. So today's lecture is qualitative and will contain a large number of animations about, we will try and visualize at least about 5 to 10 different molecules, small to large, and let us look at, examine what are called the normal vibrational degrees of freedom. Let us first start with the simple triatomic molecule. We will play the animation for the ozone molecule. There are 3 vibrational modes. Okay. This is one of the 3 normal modes. Ozone is nonlinear, it is triatomic bent, and therefore what you have is the symmetric stretch. You see that both the bonds are stretched equally about the equilibrium, both the OO and the other OO bond. This motion is known as the symmetric stretch. If you look at the vibrations carefully, you see that the molecule does not translate, it does not seem to rotate, but the center of mass remains where it is, right in the middle. A genuine vibration, normal mode of vibration, is one in which the center of mass does not move and the atoms are displaced relative to each other in a certain fashion. Okay. Symmetric stretch is one of the 3 normal modes. Let us look at the other normal mode. This is antisymmetric stretch. You see that one bond is lengthened while the other is shortened. Therefore, in this mode, like the previous mode, of course, this is despite being ozone, that the atoms are identical, but you see that the bonds, this oxygen is different from this oxygen. This is the other normal mode in which the vibrations are stretched, the bonds are stretched due to the vibration unsymmetrically. It is called antisymmetric stretch. The third vibrational mode is a bending mode. Again, the center of mass will not move. What you see is that the molecular, the bond angle between OOO, the bond angle is shortened and back to normal and so on. So it is an oscillation about the equilibrium bond angle. This is called the bending vibrational mode of a triatomic molecule. Here this is ozone, all the 3 atoms are identical, and therefore one thing that you must note in all these 3 pictures is that with respect to the center of mass, each atom is displaced by the same extent. That is, if you think about the amplitude of vibration of each atom from its equilibrium position, if one atom moves away by a little bit, identical atoms also move by the same distance. The amplitudes of vibrations are all the same, and the frequency of all these vibrations for a given motion, all the atoms vibrate with the same frequency. Here the atoms being the same, all of them vibrate with the same amplitude, and this is an example of a normal mode. In the case of ozone, there are 3 normal modes. Let us look at the example of water. Let me stop the motion for the time being. So water with 2 hydrogen atoms, lighter atoms and a heavier atom, the center of mass is somewhere closer to the, somewhat closer to the oxygen atom here, right in the middle, where it bisects, it's on the line which bisects the bond OH bond, it's right here, and the center of mass will not move, but what you must see, even if the picture is not entirely clear, if the animation is not entirely clear, you must see that the oxygen atom moves a little less than the 2 hydrogen atoms. These are lighter and the amplitudes of vibration of these atoms are different and they are inversely proportional to the square root of the masses. See, the oxygen atom moves a lot less than the 2 hydrogen atoms. The text, what it says here is that the amplitudes of vibration of the individual atoms are not the same. The heavier oxygen atom has a smaller amplitude than the lighter hydrogen atoms, but what is important is that the center of mass of the molecule should not move during the genuine vibration. This is the, again this is a symmetric stretch since both the bonds are stretched equally, and this is an example of the antisymmetric stretch for the water molecule where one bond is shortened while the other is lengthened, and the third is of course the bending motion of the water molecule. With respect to this, the bond angle changing during this motion and then coming back to equilibrium and so on. So these are 3 different modes of the water molecular vibration. This is for nonlinear molecule bent triatomic. Okay. Now there will be lots of illustrations for many other polyatomic molecules during this lecture, but let us think about a linear molecule again as a slight variation from this, the normal modes of vibration for a simple linear molecule like carbon dioxide. All of us are familiar with that it's a linear structure with this CO bond angle being 180 degrees. Let us look at what the vibrational modes are like, the normal modes are like. Let me stop that. We will go back to the, okay, that is a fully stretched motion, and then what you have is the equilibrium bond length. So the vibration about the equilibrium position with both the oxygen atoms being stretched with respect to the carbon by equal amounts. Notice that during any stage of this vibration there is no dipole moment created, because carbon dioxide in equilibrium has 0 dipole moment, because the dipole vector this direction and the dipole vector in this direction cancel each other. But in the symmetric stretching, since both the bonds are extended by the same amount at any instant of time, there is no dipole moment for this molecule, and therefore there is no change in the dipole moment as well from its initial value of 0. This mode is not detectable by the infrared spectrum technique. Infrared spectroscopy cannot detect this mode because there is no change in the dipole moment of the molecule, it remains 0 all the time. This is a symmetric stretch. Let us look at the asymmetric stretch. Again the molecule should not move from its equilibrium position, the center of mass remains where it is. The stretch is such that one of the carbon oxygen bond is stretched while the other carbon oxygen bond is shortened, such that the center of mass remains where the right where the carbon was in its equilibrium position. And in this position you see that the stretch due to this does not give you a dipole vector which is equal to the dipole vector here. The charge separation between these two atoms will be different from the charge separation here, therefore there is a net dipole moment during the stretch, and the dipole moment increases to a certain value and then it decreases to 0, it increases, decreases, and therefore the dipole moment sort of oscillates between 0 and a certain value. There is a continuous change in the dipole moment during the vibration. This is detected by the infrared spectroscopy. Therefore carbon dioxide, despite being a linear molecule with 0 dipole moment, has one normal mode of vibration which is detectable. There are 2 other modes which I will tell you. The molecule cannot be detected by microwave spectroscopy for its rotational spectrum because it does not have a permanent dipole moment. in the limit of rigid rotor. If the molecule is not a rigid rotor but it is a semi-rigid rotor with the vibrations taking place, you see that the moments of inertia keep changing, dipole moments are created, and therefore we have problems. Okay. Pure carbon dioxide in the limit of rigid rotor approximation does not have a microwave spectrum, but one of its vibrational degrees, as you see here, has a vibrational spectrum because the dipole moment is created and destroyed. It oscillates between different values. There are two other modes for carbon dioxide. It is a linear molecule, 3n minus 5 for n equal to 3, linear is 4, two of them you have seen. It is a third one which is the bending in such a way that the carbon balances the bending of the two oxygen atoms such that the center of mass remains where it is. And again in this bending the dipole moment vector, as you see it, in this bending the dipole moment vector is created with the plus charge and the minus charge here, plus and minus here, and therefore the sum of these two dipole moment vector is that. It is not 0, actually it should be exactly the same as the diagonal of the parallelogram that you have. Sorry, let me erase that. If these are the two dipole vectors, then you draw a parallelogram. The total dipole moment vector for the sum is that. Okay. Therefore, the dipole moment is 0 when the bond is like that. When the bond is like that, the dipole moment is small, and when the bond is bent to its full extent possible under the small amplitude motion, then you see that the dipole moment keeps increasing and then it decreases. It decreases to 0 when it goes up. Therefore, there is a change in dipole moment. So this is an oscillatory motion, bending mode, for which the dipole moment changes. It can be detected by IR spectroscopy. Okay. There is one more bending mode which has the same energy. It is called the degenerate bending mode to that. This bending is that the molecule is going into the plane of the screen and out back onto the screen. So it is going to the, if you are watching this in the television screen, it is like going to the back of the television screen and then coming back to the front. So this is another bending mode. Again in this bending mode dipole moments are created and its value keeps changing during the oscillation. Therefore, this is an oscillating electric dipole that is present in the molecule. This is also detected by the infrared spectroscopy. What is important to note is that this bending is only in two different planes. Here the plane is the plane perpendicular to the plane of the screen. Here the plane of the motion is the plane of the screen. Therefore, they are both degenerate. The molecule does not know what the plane it is oscillating. It is a triatomic molecule, and our association of axes is for us to visualize various different possibilities. Energetically both these motions have the same energy and therefore they are degenerate. These are the 4 normal modes of vibration for carbon dioxide molecule. Now let us go and define the normal vibrations a little more quantitatively.